cardiovascular diseases represent the world's leading cause of death. Medical researchers assume a strong correlation between the initiation and progression of cardiovascular diseases and abnormal flow characteristics such as vortices. To investigate the influence of vortices on cardiovascular diseases, medical studies with homogeneous patient groups are performed. The vortex occurrences are counted and classified according to specific characteristics. Such a vortex classification is manually performed with common flow visualization techniques, such as a 3D pathline view embedded in the vessel surface. The vortices are classified according to their shape, which is divided into helix and vortex depending on the extent of a vortex and the strength of its forward movement. Furthermore, their temporal occurrence is determined. Vortices occur in the systole and/or the diastole. Therefore, a pathline animation together with a time bar is used, which shows the current time point within the cardiac cycle, as well as a systolic and diastolic endpoint which were manually defined. Moreover, the vessel sections were identified. Therefore, the aorta is divided into 4 parts: the ascending branch, the ascending arc, the descending arc, and the descending branch, which are color-coded here on the center line. The vortex size is divided into minor and pronounced, depending on if the vortex occupies on average more or less than 50% of the vessel diameter. The rotation direction is divided into left and right-handed flow, with the center line as a reference. The manual classification is a time-consuming, subjective, and error-prone process with a high inter-observer variability. For example, the determination of the vortex size is very complicated, because the domain expert needs a lot of interaction to see the vortex from all sides, and it is difficult to estimate the distance to the vessel wall. Thus, we present a semi-automatic vortex flow classification called AVOCLA, according to the 5 properties: shape, temporal occurrence, vessel sections, size, and rotation direction. The vortex classification requires a precise definition of spatial temporal vortex entities. For this, we use an agglomerative hierarchical clustering that determines an appropriate cluster number automatically. However, this clustering allows a fast exploration of different cluster numbers if the calculated number is not appropriate. Moreover, the domain experts can merge individual clusters by simple interaction techniques. The domain experts should also be able to incorporate their knowledge during the classification process. They can manually correct the calculated vessel sections by changing the length of the aortic arc or moving the cast point. Moreover, the calculation of the systolic and diastolic endpoints based on the flow curve can be corrected. Both endpoints can be shifted by clicking into the diagram. For each clustered vertex, AVOCLA calculates the 5 properties automatically. and depict them using a tabular representation. The colors of the vertices correlate with the colors of the table columns. The results should reflect the binary expert classifications. However, these binary classifications are not always appropriate to describe the vertex behavior. For example, in most cases the vertex shape take on an intermediate shape between helix and vertex, such as the brown vortex. Thus, AVOCLA's results should extend the binary classification. Therefore, we calculate the percentage of helical and vertical flow per vertex. Intermediate shapes show very similar flow components, whereas a helix or a vertex has a stronger helical or vertical component, respectively. Besides a tabular representation, the experts want an adequate visualization of the classification results, in order to verify and interpret them better. Therefore, we developed a 2D plot and a 3D glyph-based visualization that show the calculated vertex properties. The 2D plot allows an occlusion-free depiction of the spatial temporal vortex behavior. The temporal component of each pathline point is mapped to the angle, whereas its spatial position is mapped to the radius. Each plot segment is colored according to the cluster portions, at which red time points represent the systole and blue time points the diastole. For example, the blue vertex occurs during the systole in the ascending branch. The 3D glyph-based depiction shows the radial expansion and rotation direction of the vortex. Therefore, we determined the surface that envelops the vortex, whereupon both properties are mapped. The radial expansion is visualized using a linear color scale. Areas that occupy less than 50% of the vessel diameter are mapped on the blue gradient, and otherwise on the red gradient. The rotation direction is depicted by arrows on a quad strip around the surface. For a right-handed vortex, such as the blue one, the arrows point in flow direction to the upper right. In the case of a left-rotating vortex, such as the brown vortex, the arrows point in flow direction to the upper left. To generate a correlation between the 3D glyph and 2D plot visualization, the arrows get the cluster color. In summary, AVOCLA allows an objective vertex description and leads to a decreasing inter-observer variability. The 2D and 3D vertex visualization facilitate the interpretation of the calculated vertex properties.